So let's take an example of the type x dot. I use the same example, 2x plus 2y, and y dot equals to x plus 3y. And let's say there are certain initial conditions. X of 0 is 2, y of 0 is 1. So what we want to do is to try to solve the system. If you just keep in mind what we've been saying all along is that we may not be able to solve the system explicitly for x in terms of y. Sometimes it's not possible. Here, it's debatable. At the end of the discussion, we'll discuss whether we can solve it or not. But in most cases, you can't. So the next best thing is to get phase portraits to see what the solution curves look like by using other extraneous factors. The one factor that we learned to use was eigenvalues and eigenvectors. With help of eigenvectors, we were able to see what the tendency is to draw spirals, nodes, several points, and so on, just by looking at gradients and those eigenvectors. Now, yesterday I discussed another piece of information that can help us, that's called NULLCLINES. So let me develop this a bit. NULLCLINES. Okay, well, just for some information, if you have to solve, let me just write it as we do it completely. If you were to solve this whole problem, you first need to find the eigenvalues and eigenvectors. So the matrix here is 2, 2, 1, 3. I'm using the same one from yesterday because it's not easy to find these ones for a certain purpose. I can't just put 4 numbers down and hope that it'll give me a simple one. It might give you complex roots and stuff. So just bear with me. I'll use the same one. So you'll find the eigenvalues are lambda equals to 1 and 4. And when you compute the eigenvectors, E1 works out to be minus 2, 1. And E4 works out to be 1, 1. So that's normally useful. So what we've learned so far is that if you draw those two guys in at least, minus 2, 1. So if you take 1 minus 2 somewhere here, minus 2, 1. Sorry, minus 2 is here, 1 is there. So this line here is one of the eigenvectors. The eigenvector just gives us the direction to start. The other one is 1, 1. Take 1, 1. So that will be y equals to x. This here is 1 over minus 2, so it's y equals to minus half x. And both eigenvalues are positive, plus 1 and plus 4. So it follows both are going outwards from the center. And these arrows also tell us where the flow lines will tend towards. So the solution will be x, y will be like C1 minus 2, 1 e to the t plus C2 with the constants 1, 1 e to the 4t. And the arguments work around the fact that e to the 4t dominates at infinity. So the tendencies will be to approach e to the 4t. So even if a curve leaves 0, 0 here, if it leaves in that direction, at some point it will have a change of mind and move like that. So it becomes like parallel to that line. Even if a guy is leaving there, he'll go like that. Likewise here. The guy is leaving here. He'll eventually twirl around and become like that. This is just an unstable node. unstable node. All lines that move towards, so even these lines here, this line here, if it wants to go towards minus x over 2, it will, and then eventually it'll go that way. It'll curl towards y equals to x. Like this guy here wants to go like that, but it'll curl downwards this way. So that's what we call the phase portrait for a two-dimensional linear system. Now, that's easy enough. There's not much more one needs to compile that. But let me show you now how we use NULLCLINES, how we can add to the conversation. And in some cases, it's the only way to do it. This thing doesn't work because you can't find the eigenvectors. Remember, one case for eigenvalues is where both are complex. So the eigenvalues are complex, the eigenvectors will turn out to be complex also. Now, how do you plot an eigenvector that's complex with complex numbers? You can't. This is a real number plane. So then you're almost stuffed with it. Then you can use the other method I showed you where you take points all over the place, lots of dots, and work out the gradients. The gradients will give you the hint which way they are flowing. But NULLCLINES is a useful technique. So let me talk about NULLCLINES. NULLCLINES. These are when x dot is naught and y dot is naught. This will become relevant in the sequel when we go on to non-linear systems. Game gets much harder, by the way. But if you follow the easy game, then the hard game is the same kind of thing, just another level. What is added complication? The added complication in the hard game would be two fixed points. So far, there's only 1, 0, 0. Very convenient for us. But when there are two fixed points, now things will start to behave. You might get a spiral there and something else happening here. But if you understand each one separately, it'll make it easy later on. So why these are important is because the gradient is actually y dot over x dot. And it's like dy dt over dy dx dt, which boils down to dy dx, which is the gradient. If you're plotting things in x and y, dy dx is the gradient. If you take a look at that guy, the green one, you can see if y dot is 0, then m is 0. Then you're talking about a horizontal gradient. We're talking about vectors that are horizontal. If the gradients are 0, then it's horizontal. On the other hand, if x dot is 0, look at the green guy, then the gradient is infinite. You're dividing by 0, that's infinite. The meaning of that is vertical. We use that now to help us to draw some plots. So I'm not going to use eigenvectors anymore. I'm just going to use these guys. NULLCLINES. Let's take the same example. X dot equals to 2x plus 2y. Y dot equals to x plus 3y. So the NULLCLINES y dot equal to 0 implies x plus 3y is 0. Which means that y is minus x over 3. It's straight line. The other NULLCLINE is x dot equal to 0. This guy here is the horizontal. This one here is 2x plus 2y is 0. Whence you get y equals to minus x. So we got these two new objects called the NULLCLINES. Let's see how they can be used now. So remember, I'm not plotting the eigenvectors anymore. Well, sometimes you have to. Sometimes you have both pieces of information. Like in this question, you can have both. But what I'm saying is sometimes you can't use eigenvectors. And like with a complex value, eigenvectors won't help you. This graph is minus x over 3. So it's got a gentle gradient like this. Are you protesting or are you I'm not sure whoever comes in here is a protester. I'm always afraid. I'm thinking of giving up teaching now because I've had enough of this environment. We should get other people to teach young people. We need to go back to our offices and do research and write about science. Teaching is a hazardous job. This one here is y equals to minus x. This is minus x over 3. Okay, so these are the two objects. For those of you that came in late, there's a new trick. In the past, we were using eigenvectors only. Now, the new trick is called NULLCLINES. Show you the top of that. NULLCLINES is when x dot is 0, y dot is 0. Why is that important? Because if you take y dot and the x dot, it's actually gradient. dy dx. Gradient. So if the numerator is 0, the gradient is 0. If y dot is 0, gradient is 0. So you're talking about something that's horizontal, no gradient. On the other hand, if the x dot is 0, the denominator is 0, you're dividing by 0, that's infinite. That means a vertical gradient. So the two lines where this happens, so each one will give you, like, if x dot is 0, 2x plus 2y is 0, and y equals to minus x. Right? Y dot is 0, means that x plus 3y is 0. That's y equals minus x over 3, that's this line here. Those are the two lines. That's where the conversation is now, right? So, let's see what happens on these lines. On these lines, you'll either have a vertical, so on these lines here, minus x over 3, so this is vertical. So on this line here, you would have, on y equals to minus x, you would have things like this. The gradients would be like vertical. At the moment, I don't know which direction they should be pointing. Where should the arrows go? But I know it's going to be vertical there. On the other line, things are going to be horizontal, like that. At this point, I don't know which direction the arrows are going to point. That's when, how do you know? So far, we haven't discussed it yet. Now, let's do that. So, to make that decision, we have to take some typical numbers on the line. Let's focus our attention on this. Let's take this point here. It's y equals to minus x. A typical point there could be, say, what, like minus 4, 4? Isn't that a typical point on the line? So once we work out the behavior at this point, it'll be characteristic of the whole line, the whole piece of line. All points will behave the same. That's why we only need one test case. One test case will tell us the whole story. I mean, one per line, or per half line. So take, say, minus 4, 4. Right? Now work out x dot and y dot. X dot will be equal to minus 4, it's minus 8 plus 8, which is 0. Of course, it's 0. We know that. But we're just checking. But now y dot, this will tell us the direction. If it's plus, it'll point upwards. If y dot is negative, it'll point downwards. That's the story. So let's put minus 4, 4. Minus 4 plus 3 fours are 12. 12 minus 4 is 8. So it's plus 8. All that matters is that it's plus. So you point upwards. And now you want this pointing upwards. Likewise, they can claim all of these are pointing upwards. The whole thing, all of these will point upwards. I don't have to do any more work. The only way the thing can change is if it crosses the null clines, so that won't happen. Let's take a point here. Let's take minus, oh no, what's this, 2 minus 2? Is that a typical point there? 2 minus 2? Let's take 2 minus 2. So this is going to be, x dot will be 0, of course. Y dot will work out to be 2 minus 2, I say. 2 minus 6. 3 times minus 2 is minus 6. 2 minus 6 is minus 4. Negative. It's minus 4. That tells me that at that point is pointing downwards. So all of these arrows go downwards. The typical case. Now let's consider the other one on y equals to the horizontal ones. These are the verticals. For the horizontal, what's a nice number that we can take here? Say, if I take x to be minus 3, x is 3, y is minus 1. Is that what? X is 3, 3 over 3, y over 1. So that's a good typical point. Any point you can take. As long as it lies on the line, I mean, you must be sure it satisfies the equation of the line. So choose some multiples of 3, which are ideal. You've got x over 3. 6 and so on. So let's do a test. So say we take 3 minus 1. Now x dot should not be 0. X dot, y dot is 0 here. When we say y dot is 0, it means nothing going up, nothing going down. It's stationary in the y direction. But it's moving this way. I just need to know which way to point the arrows. If it's plus, we go to the right. If it's negative, we go to the left. Let's do a test. Put 3 minus 1 here. 2 3s are 6. Minus 2 is plus 4. So this is plus 4. Then I can confirm that this is going to be the direction here. Right? On the other side, take what? Take minus 3, 1. Minus 3, 1. X dot will work out to be minus 6 plus 2 is minus 4. So it's negative. That means I can now say all these things are flowing like that. So those are the flow lines. And what they tell us, you see now that if I put back the eigenvectors, let me stick the eigenvectors back in here. What is the eigenvectors? Y equal to x. Yeah, y equal to x. And y equals to minus x over 2. X over 1 is, so it'll be 1 minus 2, 1. So it's going to be something like this. These are the eigenvectors. That's the stuff I said we're not going to be using all the time. But this was the original stuff we know. Y equals to minus x over 2 and y equals to x. Now let me draw in red the flow lines. And you'll see how it makes sense. Remember that the fixed point is 0, 0, the center. This is the bigger eigenvalue. This was E4. If you remember, this was E4. If you came in late, you missed that calculation. This is E1, but that is a calculation you know already how to do. So we were saying that you can always approach, may start off going towards E1, and then the way to E4. Now you see this direction here. So if you goes like that, take these arrows here, forcing you to bend. That tells you it's going to bend like that. And then the fact that it's E4 means it's going to get parallel to E4. So at infinity, towards infinity, E4 dominates. E to the 4t will dominate. But this is now giving us an extra piece of data to tell us where it's bending. Yeah. Here it's not so impressive because you know what it looks like already. You may just yawn that, well, I knew this already. What's new? But you'll see with the complex values one, it is important. But this confirms that the behavior is right. That's a flow line there. The flow must be harmonious. The null-cline flow, you see here. Likewise here. Flow lines like that. These flow lines flow like that. Likewise, the flow lines are like that. And remember, these are just few flow lines. There's millions of them. These are few flow lines, but there's actually millions. Yesterday, one of the students in the class said, I think this color will play because flow lines will cover all the points. That's true, but the flow lines tell you the direction you must go, the trajectory. If you're sitting on this curve here, you know it's going to go like that. If you just see a mass of points here, you won't know where to go. But effectively, we cover the whole plane. Every point is, there's a curve passing through every point. All right, now that's the idea. Let me take another example where the idea is actually indispensable. Let's take, I wrote the solution. Let's take the next example. Example 2. This time x dot is 2x minus y. Y dot is x plus 2y. Oh, sorry, what I didn't finish there was the solution was xy equals to c1. Let me just write the solution finally there. Minus 2, 1 e to the t plus c2 1, 1 e to the 4t. This is the actual solution. The picture is just the flow lines. It tells us how we depict the solution depending on the constant c1 and c2. So there's a whole family of curves. For different c1s and c2s, you get any one of these curves. Now to write the solution explicitly, we can say x is equal to c minus 2 c1 e to the t plus c2 e to the 4t. The top row. The top row. That's the solution for x. The bottom row becomes the solution for y. So y is actually c1 e to the t plus c2 e to the 4t. solution. This part, I think this was yesterday. This guys were around yesterday. She just switch back on here. Can you write x in terms of y explicitly? Can you eliminate t, for example? Anyone? Any comments? Is it possible to write x in terms of y or y in terms of x explicitly? In other words, to eliminate the t, get rid of t. In other words, can you solve for t in one and plug that into the next one to get rid of the t? Basically, it's e to the 4t, e to the t there. Can we solve for t directly? Can we solve explicitly for t? Okay, if you just solve for c2 e to the 4t, you still got these guys. How would you kill them? You won't kill all the t's. Well, for now, let's just leave the initial values. Initial value will fix the C1 and C2. But even there, okay, let's take it. Maybe you will make the thing look easier. What did I say? X of naught is 1. X of naught is 2. Y of naught is 1. Let's just use that. Let's see if that helps in any way. Using initial values. So X of naught equals to 2. That implies minus 2c1. E to the naught is 1. Plus c2. There's all that sound there. Equals to 2. And y of naught equals to 1 implies, now look at the lower one, c1 plus c2 is 1. I can solve for c1 and c2 from this. Subtracting the 2, minus 3c1 equals to 1 implies that c1 is equal to minus 1/3. And so c2 will be 1 minus 1/3, which is 4/3. So I've got the c1 and c2 fixed up. All that tells me is that the solution is x equals to minus 1/3. It's minus 2 times c1, so it's going to be 2/3 e to the t plus 4/3 e to the 4t, and y is c1, which is minus 1/3 e to the t plus c2, which is 4/3 e to the 4t. Okay, my question comes back: can we solve for x in terms of y explicitly? Can we eliminate e to the t and e to the 4t? Yes. Very several forms of But I'll give you one thing. The answer is yes, it's possible. Not with your method. It's possible, but it's based on something else I said about how it. Okay, let's think of this here. Let's e to the t be v, and e to the 4t be v to the 4th. So you got like a v and a v to the 4th. Can you solve for v if you got a 4th power equation? One day I was doing a side show on that, where you can solve certain break equation. V to the 4th plus v equals to something, say x. Can you solve for v? Is there a formula to solve for your 4th power equation? The answer is yes. Can be done. It's very clumsy and very long calculation, but technically it can be done here. Then you find v, or e to the t at least. V, let's call it v, and you plug in here. You can put the result here and put that thing to the power 4 here. Then you'll have the x, y is equal to something x. very long in terms of, but in this particular example, can you guys can you imagine what kind of graph it would look like? It would have like fourth power, something to the power 1/4 and stuff. It's not something you normally see because they are saying, I don't even know what it looks like. Well, actually, now I know what it looks like. There's these little curves up there, portraits it. That's really what it's going to look like. Those are families of curves, but you will never guess that. But those are the families of curves that it looks like. Okay, but you can imagine, suppose this problem had an eigenvalue of 5, and this would be 5t, 5t. Then you won't even be able to solve it. As I said in my lecture there, that a fifth degree equation can't be solved. Then the answer there is no. Then only the integral curves will be useful. That's why this is a powerful idea. Okay, so what? It is possible. Yeah. All right, let's leave that. Let's take this example here now. This has got a different spin. What is the different spin here? Matrix A is 2 minus 1, 1, 2. And when you work with eigenvalues, the thing is that lambda 1 is 2 plus I, lambda 2 is 2 minus I. You can see the problem straight away. We're dealing with complex eigenvalues. And can you find the eigenvectors? The answer is yes. They will also have complex entries, which is not helpful because you can't plot the eigenvector. So now you will be totally at sea because you don't have eigenvectors. In the previous case, you had both sets of data to balance. Now you will be, but you do know from that early development that if the A is positive, it's a spiral outwards. If the A is negative, it's a spiral inwards. If the A is a 0, we call it a center. Those are in the notes from the past. If you go back, long time back, those days we used to have lectures. Like one guy sent a mail yesterday, one of your friends, I don't know who it was, maybe one of you, somebody sent a message from students saying that there are no tests and assignments and stuff. But he didn't have it quite right. He was saying, no, it was meant for students to refamiliarize themselves with studying. I think, what? If anything, people who were off were studying. What else will you do with your time? But the real reason, actually, I still don't know the real reason. This morning, the registrar writes that it's because of goodwill towards students who are striking. But earlier on in the day, the dean sent a message saying, no, actually, on the original 7th calendar, this whole week is not supposed to be used for test and exam because something about Islamic week or whatever. That was the reason. You can see when you're sitting in our chair, you don't know what's going for what. What are the reasons and what's going on here? Very hard. Anyway, I was saying, so these are complex eigenvectors, eigenvalues, sorry. What time is this period? 13:05, right? Complex eigenvalues cannot plot eigenvectors, although they exist. We know already that A is more than 0 implies a spiral. It's an unstable spiral. I'm not going to use this fact though. I'm going to do as if I don't know this, but I'm just reminding you that we do know it. Let's now compute the NULLCLINES. That's the new thing. NULLCLINES. So your horizontal is when y dot is 0. This means that x plus 2y is naught. This means that y equals to minus half x. The vertical is when x dot is naught. This means that 2x minus y is 0. or y equals to 2x. So if you look at the picture with the null clines in it, y equals to minus half x, it's something like this. And y equals to 2x, it's something a bit steeper like that. But these are just null clines. They're not eigenvectors. They give us an idea of the direction of flow. So we take some typical numbers. Let's take a number here, like say, what, like 1, 2. So these are vertical. These are horizontal. So let's take the vertical first. Let's take 1, 2, and put it in y dot. Y dot works out to be x plus 2y. So it's 1 plus 4. So it's going to be 5. It's positive. So it follows all of these are pointing upwards. If you take something down here, say minus 1, minus 2, y dot will be equal to minus 1, minus 2 is minus 5. So these guys are pointing down. Right? Likewise, if you take the horizontal ones, you take a number here, say 2 minus 1, x dot, which is 2x minus y, will be 4 plus 1 plus 5. Hey, all the answers are 5. So this thing is flowing that way, plus 5. You take a number on this side, say minus 2, 1. X dot will be minus 2, minus 4, minus 5. So you can take any number that lies in the line. That's all I have to go with now. From zero, things have to go leave somewhere. You have to flow in this direction for a while. But somehow you have to curl this way. And they also have to go that way, meet that gradient, and around by that. That's what we call a spiral. So if I got a guy starting here, oh no, that's a bit clumsy. Oh man, that's not what I want. And then this guy leaves here, follow this path here, like that. That's one example of a spiral. You can see the arrows. Follow the arrows that are there. That's just one example. I mean, you could have many other examples. Another one could be like that. So yesterday somebody was saying, but in the class, why did you draw just a bit of it? Yes, in the notes I've drawn the spiral like this. It's the same thing. You got your two. Remember, these are not the eigenvectors, so they don't tend towards these lines. I think I drew it like this. That's a spiral, yes, true. The Milky Way is like that, the universe that we live in, the spiral galaxy. But these are just a few of the stacks of the spiral. This one is like this. It's going to go around like that. It's going to look like that if you look at the big picture. let's stop here, but next time I can even show you a mathematical plot of this. Finish the class.